Okay, so welcome again to the channel. So in this case, I'm going to reuse this model here, using plate or shell elements. This is actually, you can find this one in YouTube, okay, or in here. And this is using shell. So instead of starting from zero, what I'm going to do is extrude these 2D elements throughout the thickness to make them solid. So let's just do it. So here we are, file, open, see solid. This is the model from before. So in here, if you look at it on the model, we should have just plate elements, okay? But let me delete some other stuff here. All right, we need to delete as well the loads and the constraints. It would be good to delete the analysis, the results. And why not the analysis? That way we'll know exactly what will be happening. Okay, Control A, that looks too white. So we have the surfaces here. Maybe I can turn on this plus the elements. The elements are off. Let's see if we can do this. All right, so basically you see this has no thickness, so this is the plate elements. Before, in order to show they had thickness with this, all right? But let's remove it. So in order to do that, what we need to do is to create a new property here. And that new property is going to be solid. So you can call it solid property. All right. And now what we do is mesh, extrude elements. So we're going to select all these plate elements. And we can choose different options. Let's say we're going to do 2 elements throughout the thickness. And we can use a long vector to surface. There's no surface. Let's try this one. So delete original. Okay. So length 1, 2 elements. Okay. And here we should see the thickness showing up like right here, if we did it properly. Okay, so we got now solid elements. Let's check the edge, see if we have 2 elements. It looks like we have 2 elements throughout the edge. Okay, 1, 2. All right, so now what we need to do is F8 XY top. Okay, all right. Apply the constraints, so model, constraint model, boundary conditions, BC. Okay, pick box, and come over here. Do this, and okay. And here we don't need to do fix, because since there's 3, okay, if you hold something by 2 parts, it won't be able to rotate, okay? And here we have even 3 nodes, okay? You see here, 1, 2, 3. So fix, okay. Control A again. F8, XY top, okay. Now from here to here, you have 41 nodes, and we have 3 elements throughout the thickness, so we need to multiply by 3. So model, constraint, no, load, model. So this is the force equal 400. Okay, pick box. And we're just going to pick this one here. So basically what we need to do the 400 force. We need to divide it among 41 nodes. And we need to do that 3 times because it's 3 rows of them. All right, so that gives you here 3.252. And that should be it. So file, rebuild, yes. Let's create analysis, manage new, static, next, 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 next. I'm just going to activate something in case we get some weird result. The equation force of the first balance Basically, this will help us to sum all these forces and see if they are really 400. But I don't know if we need it. So analyze. Okay, so it's done. Oops. Results. Okay, F5. And if you remember properly from the previous video, we should get about a factor of 3, so 3 times the stress here compared to the far field stress over here. So we should have like some red over here close to value 3, and here some blue far away close to the value 1. So contour, deform. We can look at the von Mises, but we probably can look at the normal stress. And okay. Okay, so that's pretty good. You see here, this blue will be about 1. All these blues will be close to 1. And the stress can deactivate the node, should be close to 3 right at the top here and the bottom, which is what we get right here. Okay, let me remove this so we can see through. Okay, so it's the background here that is still. So I don't know if we need to do anything else. I think that's pretty good over here. Okay, maybe let's go to F5, deform and von Mises, but we should get basically exactly the same thing. We got 2.293, okay, 2.966. What happened is that these ones will be more uniform here. So I think that's it, okay? If you want to look the values for the comparison of 3, I did introduce those videos on the that data on the shell, but we can go very quick if you want. Let's see, plates. Not sure if I showed this document before or not, but basically I got this one from online. It's closed form solution of some different cases. And here you see stress around a circular hole. They do derive the equation in polar coordinates, and basically they get here the expression for the 3 of them. So basically you see what happened is that when this angle here, let's say will be, if you go around the circle, so the circle will be this one. So if it's 90 degrees, 180 will be right here. And you know that for the cosine, this is cosine of 0 is 1, cosine of 180 will be minus 1. So we come here, we get what? Is 1 plus minus 1 hold on one second here. I see something strange. Okay, here we go. As shown in figure 3 is over here, we get that the maximum stress is 3 sigma the periphery of the hole, okay, right at the top. And this is coming, this should be coming from this equation here. Okay, so let's look over here. What would happen? This will be sigma, this is 1, so 1 plus 1. Okay, at the periphery will be 2, so this is 1 sigma. And then this one will be, all this will be minus 1, so it becomes positive. And here we have 1 plus 3. Okay, because this is 1. So that will give you 3 plus 1, 4, divided by 2 is 2, plus the 1 we have over here, which gives you the 3 over here at 90, okay? Which is what we have over here at 90 degrees. This value here should be 3 times the value over here, which is about 1, and right at the top and the bottom at 90 degrees is about 3.